let's continue. Okay, let me open the table of content first. Okay, so we are still in chapter 20, paging smaller table. On previous session, we already take a look at multi-level page table, and now let's take a look at the inverted page table. Alright, let me open the chapter. Yeah, there's mosquito again. Okay. Alright. Yeah, previously we already take a look at this one, multi-level page table. Okay. Alright. Okay, now let's take a look at this inverted page table. An even more extreme space saving in the world of page table is found with inverted page table. Oh, there's even more extreme technique. Oh, okay. Here, instead of having many page tables, one per process of the system, we keep a single page table that has an entry for each physical page of the system. We keep a single page table that has an entry for each physical page of the system. The entry tells us which process is using this page and which virtual page of that process maps to this page. Okay, wait a minute. We keep a single page table that has an entry for each physical page of the system. Oh, is it like the linear page table, but instead of one linear page table per process, we have one linear page table for the entire physical memory? Is that it? Maybe. Yeah, I'm still not sure. The entry tells us which process is using this page. And which virtual page of that process maps to this physical page. Okay, finding the correct entry is now a matter of searching through this data structure. A linear scan would be expensive, and thus a hash table is often built over the base structure to speed up lookups. Okay, the PowerPC is one example of such architecture, an architecture. Okay, more generally, inverted page table illustrate what we have said from the beginning. Page tables are just data structure. You can do lots of crazy things with data structure, making them smaller or bigger, making them slower or faster. Multi-level and inverted page table are just two examples of many things one could do. Alright, now section 20.5, swapping the page table to this. Okay, finally we discussed the relaxation of one final assumption. Thus far we have assumed that page table reside in kernel own physical memory. Even with our many tricks to reduce the size of page table, it is still possible, however, that they may be too big to fit into memory all at once. Thus, some systems place such page table in kernel virtual memory. In kernel virtual memory. Okay, thereby allowing the system to swap some of this page table to this when memory pressure gets a little tight. Thereby allowing the system to swap some of this page table to this when memory pressure gets a little tight. We'll talk more about this in a future chapter, namely the case study on VAX or VMS. Okay, I'm still not sure what this is yet. Once we understand how to move page in and out of memory in more detail. Okay. Move page in and out of memory. Alright, now the summary. We have now seen how real page tables are built, not necessarily just as linear array, but as more complex data structure. Not necessarily just as linear array, but as more complex data structure. The trade-off such table present are in time and space. The bigger the table, the faster a TLB miss can be serviced, as well as the converse. And thus the right choice of structure depends strongly on the constraint of the given environment, as well as the converse. Wait a minute. I wonder what the converse in here means. Okay. Oh, maybe some kind of translation. Yeah, the bigger the table, the faster the TLB miss can be serviced, as well as the maybe the translation from the virtual memory to physical memory, the virtual address to physical address, maybe something like that. And thus the right choice of structure depends strongly on the constraint of the given environment. In a memory constrained system, like many older systems, in a memory constrained system, okay, like many older systems, small structure makes sense in a system with a reasonable amount of memory and with workload that actively use a large number of bits. In a system with a reasonable amount of memory and with workloads that actively use a large number of bits. In a system with a reasonable amount of memory and with workloads that actively use a large number of bits, a bigger table that speeds up TLB miss might be the right choice. Oh, wait. In a memory constrained system, small structure makes sense in a system with a reasonable amount of memory and with workloads that actively use large number of pages. A bigger table that speeds up TLB miss, the translation look aside buffer miss might be the right choice with software minutes TLB, the entire space of data structure open up to the delight of the operating system innovator. Hint, that's you, okay. Entire space of data structure open up to the delight of operating system innovator. Yeah, with the software minus TLB. What new structure can you come up with? What problems do they solve? Think of this question as you fall asleep and dream the big dreams that only operating system developer can dream. Oh, okay. I am not sure what operating system developer dream is about, but yeah, it is what it is. Dream the big dream, something like that. Okay, reference. Computer system a programmer's perspective. We have yet to find a good first reference to the multi-level page table. However, this great textbook by Brian and O'Halloran, I probably mispronounced that, dive into the details of x86, which at least is an early system that uses such structure. It's also just a great book to have. Okay. Virtual memory issues of implementation. An excellent survey of a number of different systems and their approach to virtualizing memory. Plenty of detail on x86, PowerPC, MIPS, and other architecture. Virtual memory management in the FAX or VMS operating system. Oh, is VAX/VMS an operating system? Interesting. A terrific paper about a real virtual memory manager in a classic operating system. Okay, VMS. So terrific, in fact, that we will use it to review everything we have learned about virtual memory thus far, a few chapters from now. Okay, so VMS is the operating system. Alright. Reese peanut butter cups. What? Apparently, these fine confection were invented in 1928 by Harry Burnett Reese, a former dairy farmer and shipping foreman for one Milton S. Hershey. At least, that is what it says on Wikipedia. Okay, if true, Hershey and Reese probably had each other's guts. What? As any two chocolate barons should. Okay. Yeah, like, what is this reference mean? I'm not sure. Practical transparent operating system support for super page. Oh, what is super page? Okay, a nice paper showing all the details you have to get right to incorporate large page. Oh, a nice paper showing all the details you have to get right to incorporate large page or super page into a modern operating system. Not as easy as you might think unless... Okay, wait. So this is the paper to incorporate large page, or called super page. Interesting. I mean, in the, what is it called? One of the aside, I guess. Not this one. Oh yeah, maybe this one. There is some cases where we have multiple page size, you know. Where is it? This type of large page usage or super page, maybe that's what it is called. This type of large page usage is common in database management system and other high-end commercial applications. The main reason for multiple page size is not to save page table. However, it is to reduce pressure on the TLB, the translation look-aside buffer, enabling a program to access more of its address space without suffering from too many TLB miss. Right? However, as researchers have shown, N plus 02 using multiple page size makes the operating system virtual memory manager notably more complex, and those large pages are sometimes most easily used simply by exporting a new interface to application to request large page directly. And plus 02, okay, let's take a look at that reference. Oh, this one. Okay. Transparent operating system support for super page. Okay. Multex history This amazing website provides a huge amount of history on the Multic system, certainly one of the most influential systems in operating system history. The quote from therein, Jack Dennis of MIT contribute influential architecture ideas to the beginning of Multics, especially the idea of combining paging and segmentation. From section 1.2.1. Alright. Okay, now we have this homework simulation. This fun little homework test. If you understand how a multi-level page table works. And yes, there is some debate over the use of the term fun in the previous sentence. Yeah, there is some debate. Alright. Can we call this fun or not? Yeah, that is debatable. Right. The program is called, perhaps unsurprisingly, Paging Multi-Level Translate.py. See the readme for the task. Okay, before we continue to the question, let's take a look at the Python script here. Like always, yeah, be sure to check the script content before running the script. Okay, converting. Right, and then rounding up. Okay. Oh, we use class. Okay. Alright, this is the information. Oh, okay. Around 200 line. No page use. Alright. Append to memory. Okay. Associative array. I assume this is the page directory base register. Alright. This is the max. Oh, interesting. Okay, that is the base directory entry max, and then this is the shift. Oh, 10-bit. Okay, we are shifting 10-bit. Alright, so we only, what is it, get 5-bit here, I guess. This is the page table max. Page table shift is 5-bit. Okay. Interesting. This is the virtual page number max. The combination of the page directory max and the page table entry max. Okay. and then shift, and then the virtual page number shift is the page table entry shift, which is 5 bit, I guess. Okay, offset max. Grab the last 5 bits of a virtual address. The last 5 bits, okay. So I assuming the first 5 bit is the base directory, I guess. And then the second 5 bits is the page table entry, and then the last 5 bit is the offset. Maybe something like that. Find free. Okay, use page count. Random, okay. Use page. Oh, right. We add the use page here. Okay. Okay, we adding page, I guess, in this case. Alright. Init page directory, something like this. Oh, there's page speed. Log of page size. Okay. So 1 page is 2 power 5. 32 byte. Okay. Alright. With byte. Okay. Yeah, this is initialize page directory. Oh, interesting. To initialize the page table, we initialize the page directory, and I guess also initialize the rest. Maybe this is get the page table entry. Right, shift with the page tables entry shift, and then add the bits there. Okay. Valid. Oh, 7. Interesting. We read shift by 7 bit. Okay. And then the page frame number, something like this. Print stuff equal true. PTA contents. Okay. Get page directory entry. Okay. Set page table entry. Alright. Okay, set page table entry, set page directory entry. Okay. Unlock virtual page. Make it into a virtual address as everything use this and not virtual page number. Okay. Get page directory entry. If valid equal 0, must allocate a page of the page table now and have the page directory point to it. Alright. Save page table entry. Okay. Negative 2 equal page table entry fault. Alright. Negative 1 means page directory entry fault. Alright. So this is, I guess, invalid page directory entry. It means there is no, what is it called? There is no allocation in the page inside this page directory. And for this one, well, it is not allocated to for the page table entry. Maybe something like that. Okay. Wait, let me check this. Oh, okay. From this one, the validness. Okay. Fill page. Alright. Proc unlock. Is this the process allocation? Is that it? Need a page directory base register. Find somewhere in the memory. Okay. Right, find free here. Oh, yeah, there is the process ID. Okay. Then this one allocated virtual page, I assume. What this mean? Virtual page. Oh. Okay. Replace that. Use virtual page. Oh, we fill up use in this iteration. Okay. Right. If use FP here is 0, withdraw an assertion, or not 0, I guess. I'm kind of forgot. assert. I mean, is this the condition that will fail with the assertion, or the assertion will throw an error if this condition does not meet? That's what I'm not sure. Let's take a look at this then. Expression. Okay, can be any valid Python expression. If expression is false, then the statement throw an assertion error. Okay. So if the use fp here is not 0, then we throw an assertion error. Something like that. Right, not this one. Okay. Allocated virtual page append. Okay. Oh, so the expected here we are making this 0. Interesting. And if it is other than 1, we throw an other than 0, I guess. We throw an assertion error. Okay, find free. Dump page. Okay. Memory dump. Get base directory, base register. Okay, get value, allocate some process in memory, allocate some multi-level page in memory, make a bit of a mystery. Can examine page directory base register PFN or the page frame number of current process page directory. Can examine contents of any page, fill page with values to, ask when given, load virtual address. What is R1? What will final value will be loaded into R1? Is R1 the register? Something like that. Okay, this is the option, I guess. As usual, the random seed, the allocated option, number of virtual page allocate. Okay, address, number of virtual address to generate. Okay, and then you compute answer, right? Okay, parse First argument, alright. Memory dump. Base directory, base register, okay. This means the base directory is held in this page. Okay. If solve equal true, we print this out. Otherwise, this one, virtual trace translate to what physical trace and fetch what value or fault, right? Okay, there is that. Oh, did I have this note? I didn't realize that. Okay, I need to move this note later on into my other notes. Okay. This one little homework test. This one little homework test if you understand. This one little homework test if you understand how a multi-level base table works. And yes, there is some debate over the use of the term fun in the previous sentence. The program is called Patching Multi-Level Translate.py. Okay, some basic assumption. The page size is an unrealistically small 32 byte. The virtual test space for the process in question, assume there is only one, is 1024 bits or 32 kilobyte. Physical memory consists of 128 bits. You know what? Let's continue this on the next session. Yeah, let's read this readme on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.